Assalamu alaikum students. Welcome to the sixth lecture of operating systems. We continue the chapter called Uniprocessor Scheduling. Please refer to chapter 9 of the book by William Stallings. In the last lecture, we elaborated on the three types of processor scheduling. We talked about various scheduling criteria and discussed examples that were relevant to them. We understood the queuing mechanism that enforces priorities. We defined and explained starvation. Now that we have understood what uniprocessor scheduling is, let us take a look at the different algorithms that exist for uniprocessor scheduling. The first scheduling algorithm that we want to talk about is first come, first served or FCFS. It is also known as first in, first out or FIFO. The first one to come is the first to be selected for execution. The more you wait in the ready queue, the greater is your chance of being selected. FCFS is fair. Processes are executed in the order of arrival. It is non-preemptive. Preemption means taking the processor away from a process forcibly. In non-preemptive algorithms, the process willingly leaves the processor if it has completed execution or if it wants I/O. Nobody takes the processor away from the process without its consent. There is no starvation in FCFS. In order to make you understand how a scheduling algorithm works, I am going to use it to schedule an example workload, which is shown on this slide. There are 5 processes: A, B, C, D, and E. This table lists their arrival times and their service times or running times or execution times. A arrives at 0 and requires 3 cycles of the processor or 3 seconds on the processor. B arrives at time instant 2 and it requires 6 seconds. C arrives at time instance 4 and requires 4 seconds. D arrives at time instant 6, requires 5 seconds of execution time. And E arrives at time instant 8 and requires 2 seconds of execution time. This example is going to be the same for all scheduling algorithms. Every time I will begin by showing you this table and then we will move forward. At time instant 0, A enters the system and it is the only process there. So it is given the processor. B comes into the system at time instant 2. But remember, FCFS is not preemptive. So A continues until it finishes at time instant 3. B starts executing at time instant 3 and executes till time instant 9. During this time, processes C, D, and E all have entered the system. A has finished, B has finished, and C was the first one to come among C, D, and E, so it gets the processor and runs for 4 seconds. When C finishes, D is selected because it came first between D and E. So D gets the processor for 5 seconds. When D finishes, E is the only process remaining in the system. It was also the last one to come. So it is given the processor, it runs for 2 seconds and finishes off. The turnaround time of a process is calculated by subtracting its arrival time from the time instant when it finished execution. Here we look at the individual turnaround times of processes and the average turnaround time. A finished at 3 arrived at 0. So the turnaround time is 3. B finished at 9, arrived at 2. Turnaround time is 7. C finished at 13, arrived at 4. Turnaround time is 9. D finished at 18, arrived at 6. Turnaround time is 12. E finished at 20, arrived at 8. Turnaround time is 12. How do I calculate the average? 3 plus 7 plus 9 plus 12 whole divided by 5. The average turnaround time comes out to be 8.6. If many long processes arrive early, a late short process must wait a lot. So in FCFS, late arriving short processes tend to suffer. If many CPU bound jobs arrive early, a late IO bound process must wait a lot. Even when the CPU bound jobs are not using IO. So in FCFS, IO bound jobs tend to suffer. But this suffering of short processes or IO bound processes will not be considered starvation. Why? Because this is happening because these processes are arriving late in the system. The algorithm is not mistreating them. The algorithm is not unfair in its working. They are suffering due to late arrival. The second scheduling algorithm is round robin or RR. It is the combination of FCFS and preemption. It is also called time slicing. It is preemptive. Preemption is based on a clock. A clock interrupt is generated at regular intervals. This interval is called a quantum. The running process is preempted from the processor at the expiry of the quantum and placed at the end of the ready queue. A process can either leave the processor willingly if it completes or asks for IO, or it will be preempted when its time is up. The smaller the quantum, the greater is the switching overhead. Switching overhead refers to the time the dispatcher takes in selection of process. The more we switch, the greater the switching delay. So small time quanta lead to a lot of dispatching, which deteriorates performance. RR is fair. Whoever arrives first is executed first. All processes are preempted after the same length of time. Because we are making the selection very frequently, late processes do not suffer because of their arrival times as in FCFS. There is no starvation in RR. Here is my OS based take on Snow White's evil stepmom. See what has become of me. I am writing poems for you, my students. So once again, we start with our example workload. This time, we are going to use the round robin scheduling algorithm. At time instant 0, A is the only process in the system. So it is selected to be given the processor for a time quantum of 2 seconds. A runs for 2 seconds. Then the time quantum expires and B arrives in the system. The system takes A off the processor, puts it in a queue, makes a note that only 1 second of A's execution is remaining, then gives the processor to B. B runs for 2 seconds, then its time quantum expires. At the same instant, C enters the system. The system puts C at the end of the queue. B is switched off the processor and placed in the queue behind C. B still has 4 execution units remaining. A is taken from the head of the queue and given the processor. A runs for 1 second and finishes off. C is taken from the head of the queue and given the processor for 2 seconds. At time instant 6, D arrives in the system. The system puts D at the end of the queue. C is switched off the processor after 2 seconds and placed at the end of the queue. C still has 2 execution units remaining. B is taken from the head of the queue and given the processor for 2 seconds. At time instant 8, E arrives in the system. The system puts E at the end of the queue. B is switched off the processor after 2 seconds and placed at the end of the queue. B still has 2 execution units remaining. D is taken from the head of the queue and given the processor for 2 seconds. D is switched off the processor after the quantum expires and placed at the end of the queue. D still has 3 execution units remaining. C is taken from the head of the queue and given the processor for 2 seconds. C finishes off. E is taken from the head of the queue and given the processor for 2 seconds. E finishes off. B is taken from the head of the queue and given the processor for 2 seconds. B finishes off. D is taken from the head of the queue and given the processor for 2 seconds. The queue is now empty. As the queue is empty and D still has 1 unit remaining, it is allowed to run for 1 more second until it finishes off. This is the complete Gantt chart that we get when we use round-robin scheduling with a quantum of 2 units. Let us look at the individual turnaround times of our processes. A arrives in the system at 0 and finishes off at 5. Turnaround time is 5. B arrives in the system at 2 and finishes off at 17. Turnaround time is 15. C arrives at 4 and finishes off at 13. Turnaround time is 9. D arrives at 6 and finishes off at 20. Turnaround time is 14. E arrives at 8 and finishes off at 15. So the turnaround time for E is 7. Average turnaround time is the sum of individual turnaround times divided by the total number of processes, which comes out to be 10 units or 10 seconds. When a job is I/O intensive or I/O bound, it uses very small CPU bursts and then asks for I/O. After this, it leaves the processor mostly before expiry of quantum and waits. On the other hand, a CPU bound job uses its full quantum and then becomes one of the contenders for the next time quantum 2. When the IO bound job unblocks, even though it has not asked for CPU for a long time, and even though it did not use up its full quantum last time, it has the same chance of selection as a CPU bound job that is using complete time quanta and has been selected multiple times before. This results in poor IO utilization and poor performance of IO bound jobs. Consider that each Sunday your father gives 100 rupees to one of his two children. So both of you are looking forward to get the money on the first Sunday of the month. He gives the money to your sister. On Monday, you go to your grandparents' house and stay there. The next Sunday, as you haven't returned yet, he gives the money to your sister again. You return on Tuesday. The next Sunday, you find that your sister has as much a chance of getting the money as you, even though you have never been given the money before and she has received it twice. Will you be angry? Of course. The third scheduling algorithm that we will talk about is shortest process next, SPN. SPN selects the process with the shortest service time for execution. It is non-preemptive. Once a process is given the processor, it cannot be removed by the dispatcher. It will leave the processor if it completes or asks for IO. Starvation may occur in SPN. Suppose that the system receives a long and a short job. The system selects the short job. While this job is executing, the system begins to receive a steady stream of short jobs. Our system received a long job at the very beginning, but since it favors short jobs, the long job will keep waiting as long as shorter jobs keep entering the system. We say that the long job is starving. It came early, but it is being constantly ignored by the system. In SPN, long processes tend to suffer. To implement SPN, we must know the service times of processes before execution. This is not always possible. The system may use an algorithm to predict service times of processes based on their type or other historical data. Now let us schedule our example workload using SPN. At time instant 0, A is the only process in the system, so it is given the processor. B arrives at 2, but remember SPN is non-preemptive. So A is allowed to continue and A leaves the processor at 3. At 3, the dispatcher realizes that only B is present in the system. So it gives the processor to B. B runs for a full 6 seconds. During this time, C, D, and E arrive into the system. When B finishes off and leaves the processor, the shortest process in the system is E. So the dispatcher gives the processor to E. E runs for 2 seconds and then finishes off. When E finishes off and leaves the processor, the shortest process in the system now is C. So the dispatcher selects it and C runs for 4 seconds. When C finishes and leaves the processor, the only choice for the dispatcher is D. So the dispatcher selects it. D runs for 5 seconds and all the processes complete. Let's take a look at the individual turnaround times. A arrives at 0, completes at 3. Turnaround time is 3. B arrives at 2, completes at 9. turnaround time is 7. C arrives at 4, completes at 15, turnaround time is 11. D arrives at 6, completes at 20, turnaround time is 14. E arrives at 8, completes at 11, turnaround time is 3. The average turnaround time is 7.6. A big problem for designers is predicting service times for SPN. Let the actual execution time of a process in its first run be T1. For the first run, the predicted execution time S1 is not calculated but assumed. The predicted execution time for the next run is given as an average of the previous actual running times. Sn plus 1 is 1 upon n summation of Ti, where I goes from 1 to n. If you write this formula down for different values of S, you will see that S2 is T1, S3 is 1 upon 2, T1 plus T2, S4 is 1 upon 3, T1 plus T2 plus T3. All Ti's are multiplied with the same factor 1 upon n. They have the same weight in the calculation of the predicted execution time. On the left is the formula for Sn. On the right is the formula for Sn plus 1. I found the value of the summation on the left and substituted it in the equation on the right. The value of the quantity in the orange box has been taken and substituted in the equations on the right, because the quantity in the orange and yellow boxes is the same. The purple box contains the substituted value. From the working that we just did, we can write the previous equation as Sn plus 1 is 1 upon n into Tn plus n minus 1 whole divided by n into Sn. Using the above formula, the operating system predicts execution time of the next run of a process from the actual and predicted values of its previous run. We want to give more weight to the run times of the near past and less weight to those of the far past. We define a constant weighing factor alpha. 0 is less than alpha, which is less than 1. So this means alpha is a fraction. The predicted execution time for the next run is given as Sn plus 1 is alpha into Tn plus 1 minus alpha into Sn. The above equation is referred to as exponential averaging. We now rewrite the previous equation as Sn plus 1 is alpha into Tn plus 1 minus alpha into Tn minus 1 plus, and it goes on, plus 1 minus alpha raised to the power I alpha into Tn minus I plus, and it continues, plus 1 minus alpha raised to the power n into S1. Because alpha and 1 minus alpha are both fractions, each successive term has lesser weight. I have shown you an example with alpha equal to 0.8. The older the value, the lesser it takes part in the next prediction. Our fourth scheduling algorithm is shortest remaining time, or SRT. The process with the shortest remaining execution time is selected for execution. It is the preemptive version of SPN. If a new process arrives in the system re-evaluates its scheduling decision and may preempt the running process. In SRT, long processes tend to suffer because they are interrupted at every arrival. If the incoming process is short, the long process currently running is removed from the processor. Starvation may occur in SRT. To implement SRT, we must know the service times of processes before execution. The system may use an algorithm to predict service times of processes based on their type or other historical data. Now we schedule our workload with SRT. We begin at time instant 0. A is the only process in the system and its remaining time is 3. The dispatcher selects A. A runs for 2 seconds. Then B enters the system. At this point in time, the remaining time of A is 1 and the remaining time of B is 6. Since the remaining time of A is shorter, the dispatcher does not switch A and lets it be on the processor. A runs for one more second and then it finishes off. B arrived in the system at time instant 2. When A finishes off, B is the only process in the system with a remaining time of 6. Keep in mind that in SRT, preemption can take place at the arrival of a new job. So where were we? Yes, B started executing at time instant 3, but C arrived into the system at time instant 4. When C arrived, the remaining units of B were 5 and the remaining units of C were 4. Since C had lesser remaining time, the dispatcher gave the processor to C. C ran for 2 seconds. Then D arrived in the system at 6. At this point in time, the remaining time for B is 5. For C, it's 2. And for D, it's 5. Since C had the lowest remaining time, the dispatcher resumed it. C ran for 2 more seconds and completed. Also, E entered the system at 8. Now, the remaining time for B is 5, that for D is 5, and that for E is 2. Since E had the smallest remaining time, it was selected by the dispatcher. It ran for 2 seconds. Then it finished. The remaining times for B and D both are 5 now. We have just seen that there is a tie in remaining time between B and D. How do you break the tie? You break the tie using FCFS. Since B came first, it is scheduled first. So B runs for 5 seconds, finishes off. D is the only remaining job with remaining time of 5 seconds. In the end, D runs for 5 more seconds and the whole workload completes. Let us have a look at the turnaround times for SRT. A arrives at 0, finishes at 3. Turnaround time is 3. B arrives at 2, finishes at 15. Turnaround time is 13. C arrives at 4, finishes at 8. Turnaround time is 4. D arrives at 6, finishes at 20. Turnaround time is 14. E arrives at 8, finishes at 10. Turnaround time is 2 and the average comes out to be 7.2. The fifth scheduling algorithm is highest response ratio next, or HRRN. Response ratio of a process is W plus S whole divided by S, where W is its waiting time and S is its service time. The process with the highest response ratio is selected for execution in this algorithm. This algorithm favors processes who have been waiting for too long. The greater the value of W, the higher the response ratio. We say HRRN considers the age of the process in selection. The algorithm favors short processes. The smaller the value of S, the higher the response ratio. It is non-preemptive. Starvation may occur in HRRN. To implement HRRN, we must know the service times of processes before execution. The system may use an algorithm to predict service times of processes based on their type or other historical data. Now we are scheduling our example workload using HRRN. When we start at time instant 0, A is the only process in the system. How do you calculate the response ratio of A? The wait of A is 0 and the service time of A is 3. Put the values of W and S in the formula of response ratio and the response ratio of A comes out to be 1. Since A was the only process in the system, the dispatcher gave the processor to A. At time instant 2, B arrived in the system. But remember, HRRN is non-preemptive. So A continued until it finished, and that happened at time instant 3. B is the only process in the system now. The response ratio is calculated in this way. Waiting time for B is 1, service time is 6. The response ratio comes out to be 1.17. Since B was the only process in the system, the dispatcher gave the processor to B and it continued until it finished. This happened at time instant 9. During the execution of B, C, D, and E entered the system. When B left the processor, we computed response ratios of all the processes in the system. For C, waiting time is 5, service time is 4, response ratio is 2.25. For D, waiting time is 3, service time is 5, response ratio is 1.6. For E, waiting time is 1, service time is 2, response ratio is 1.5. The highest response ratio is that of C. Having the highest response ratio, C was awarded the processor. C ran for 4 seconds and finished off at time instant 13. Then we re-evaluated the response ratios of D and E. The weight of D is 7. The service time is 5. Response ratio is 2.4. The weight of E is 5. The running time is 2 and its response ratio is 3.5. Since E had the higher response ratio, E was dispatched to the processor. E ran for 2 seconds and finished off at 15. Then we re-evaluated the response ratio of the last process in the system, which is D. The weight of D is 9, the service time is 5, the response ratio is 2.8. Being the only process in the system, D was awarded the processor. It ran for 5 seconds and completed at time instant 20. Again, I am looking at turnaround times, but now for HRRN. A comes in at 0, finishes at 3. Turnaround time is 3. B comes in at 2, finishes at 9. Turnaround time is 7. C comes in at 4, finishes at 13. Turnaround time is 9. D comes in at 6, finishes at 20. Turnaround time is 14. E comes in at 8, finishes at 15. Turnaround time is 7. And the average comes out to be 8. In the sixth scheduling algorithm, which is called feedback, we do not focus on remaining service times of processes, but on how much time they have already spent on the processor. And this does not need to be predicted. The system is preemptive with priority levels from 0 to n, 0 being the highest. A new process is admitted to ready queue of priority level 0. After a process has run once on the processor, it is placed at the end of ready queue of priority level 1. The process has been demoted. After each run on the processor, a process is added to the ready queue lower in priority than the one it was selected from. Short processes use lesser quanta and are demoted less. The algorithm penalizes long processes. Starvation may occur in feedback scheduling for long processes who have been demoted to the lowest level but are not being selected because the higher queues are constantly receiving short processes. Look at this example of multi-level feedback. A system has n plus 1 priority levels from 0 to n, 0 being the highest and n being the lowest priority level. In this example, the smaller number represents a higher priority level. Each priority level has its separate ready queue. A process is added to the tail of the ready queue of level 0. When a process is taken off the processor after running once, it is sent to RQ1. After the second quantum on the processor, it goes to RQ2. Ultimately, a very long process goes to sit in the lowest priority ready queue. This means late arriving short processes are selected before early arriving long processes. So now I have a bit of homework for you. Schedule the given workload using FCFS, RR, SPN, SRT, and HRRN. Draw Gantt charts similar to what you saw in this video, but on paper and by hand. Instead of coloring boxes to identify processes, make a box and write the name of the process in the box, like the one I've shown you. A handwritten solution will be provided shortly to help you compare your work. So, what are our takeaways from this lecture? We investigated 6 different scheduling algorithms. We scheduled an example workload using 5 of the 6 algorithms, drew Gantt charts, and observed the average turnaround time. We identified the types of processes which each scheduling policy favors and or penalizes. And finally, we looked at the computations that are required to predict execution times of processes. Coming to the last slide of the lecture. Things to do. Read the book. For practice, schedule the workload I have used in my examples, drawing by hand on a piece of paper. Then check your Gantt chart with mine. Do the homework. There is no need to submit it. A handwritten solution will be provided shortly to help you compare your work and correct your mistakes. Write your questions on a piece of paper and keep it in front of you during the online session. If you have any suggestions relevant to content or quality of this lecture, email them to me. This brings us to the end of lecture 2. Did you like what we did today? I will see you soon. Allah Hafiz.